And action.
Action.
All right, so let me just turn these things on. Hold on, there we are. Does that look like me? Well, it might be me. I'm not sure if it's me. I'm in disguise. Let me see if I can share my screen, or rather, actually, let's do this. Okay, let's do that. And then let's go share. Okay, I want to share this thing here. I don't know if it'll let me. What's going on here? Share. Put a button. Okay, it's early here. It's only well, it's 6 a.m. or something like that. 9, 7. It's all right. So cut me some slack if I break up when I'm talking. Can everybody see this? Yes?
Yeah.
Looks good to me.
Good. Okay.
Yes.
Okay. So no, I'm not going to go into, I only have 6 slides and I have a bonus slide for you. So the bonus slide is something we just did yesterday or the day before, or rather, I just come to understand what the hell it actually meant yesterday. And it all relates to hydroxyl molecules. So it's worth seeing, but I only have 6 slides. So, and they're very short, right? So I spent about 30 years monitoring masers. That's all I've done. Really, I used to do star formation, theoretical. I used to fancy myself a theoretician. I am nothing like that anymore. I'm a pure observer. Really, I've gone from pure theoretical to pure observation. I can't even talk about the science of the stuff I'm doing anymore, it seems. So anyways, there we are. So that's me in a nutshell. And this is the molecule we're all talking about. And of course, if the magnetic field is non-zero, you get Zeeman splitting. And that's what this graph shows. Something that is interesting in this slide is the fact that 1720, they've actually changed the Zeeman splitting coefficient from the original value everybody was using, which is 0.236 kilometers per second per milligauss to 0.114. And that's important to me. It's basically, and I can't explain it as well as as the more theoretical people. Malcolm will do a better job than I. But I think what they've done is they've done an averaging across the hyperfine levels to give you this value versus the independent value. The fact that we're guessing at this, or not guessing, but we're educated, I suppose, is interesting to me because it tells me that the physics is not well described. In other words, we should go back and remeasure these things in a laboratory. Okay, just a thought. That's just the only reason I'm showing this slide. But basically, when you get Zeeman splitting, you get a right circular and a left circular polarization, and they really are only one maser, but they've split into 2. Okay, so if something happens to one of the masers, it obviously will happen to the other maser. And that's the whole premise of, that's the whole logic behind what I did when I was trying to find a way to use single dish telescopes to identify Zeeman pairs. And as I said to you, I'm a single dish guy and I've spent 30 years monitoring. So I'm thinking to myself, what the hell? Let's look for a method. And the answer is simple. If the RCP varies in some funky way, so too must the LCP. Maybe not exactly, but they should certainly vary because it's the same volume of gas affected, right? They're co-propagating masers. And in particular, if there's any kind of motion, then they'll definitely do the same thing. So the velocity drift in one has to be identical to the velocity drift in the other. Now, in the old sense, we started off with our spectra, and here's some lovely OH spectra from 1665 through to 6035, the excited OH lines that we can see the magnetic field easily, okay, has a large Zeeman splitting coefficient. And red is right, blue is left circular. And what you would have done in the historical times, and I say historical times, it was only, 40 years ago, but you would simply have said, okay, the brightest hydroxyl maser, left circular, and the brightest right circular were Zeeman pairs, okay? And if we go to the spot maps, which is the interferometry, which is now the accepted method of identifying Zeeman pairs, we go by location, okay? And I've circled all the Zeeman pairs that are identified in this data set on this little graph here, okay? You can see them, the numbers line up, the numbers are on the top here, and then I've circled the ones that are Zeeman pairs, right? Okay, and of course there's a problem with interferometry, and people don't talk about this very often, but of course you suffer from the possibility of line of sight confusion. So it's entirely possible that let's look at these two right here, the 1819 and the 2125. 2125 is the two brightest 6035 OH transitions, and the 1819 are the two brightest. Can't speak English anymore. I'm back to my foreign tongue. 1819 is from 6030. Okay, and so it looks like they're superimposed on each other, which is really cool, right? So and I don't know if you guys have thought about this, but if you find co-spatial molecules that are paramagnetic and they're sitting in the same volume of gas and hopefully co-propagating or something like that, then we should be able to test the physics of the molecule, right? We can test the Zeeman splitting coefficient because they have to have the exact same magnetic field. But of course, because we don't know if it's just a line of sight coincidence, we move on. So what we have to do, because I have all this data, is we have to find another method of doing that, another method of identifying Zeeman pairs that will give us a third dimension that will distinguish all of this data, disentangle, and tell you if they are in fact in the same volume of gas. And the answer to that is velocity drift. So what might you expect? And this is a graph I published in, I don't know what the year it was, but, and I want to tell you something right now, full disclosure, the paper I published on this in 2021, 2022 is actually wrong. It's actually wrong. And so the reason for me doing a lot of this analysis is because I have to correct the tables. I had not corrected for the effect of Jupiter and Saturn, and you'll see why in a moment. Because we're getting such accuracy by fitting Gaussians that we're getting down to less than 1 meter per second accuracy with the velocity. And as a result, you have to correct for Saturn and Jupiter, which are, what's it, 12.7 and 2.5 kilometers per second or something like that. And you even have to correct for the Earth having a non-circular orbit around the sun. So really, we should have included all of this in our monitoring, and I hope we are at Parkes. I know at Hartrail and at Ibaraki we are not. So I have to create a patch to correct for planetary motions in my velocity data, just as a matter of course. So I have to correct that paper. So that paper is not 100%. The premise, which is this diagram right here, is, and that is if you have velocity drift in a hydroxyl molecule, you'll get the R and L. They have to be traveling at the same velocity. Whether it's linear or not, forget about the assumption here, but whether it's linear or not, they will have the exact same velocity drift over time, okay? And if it has a magnetic field, of course, then it's going to change. If you have a constant magnetic field, it'll be the solid lines and so forth. You understand what's happening here. So then what you do is you simply de-Gauss the R and the L that you think are Zeeman pairs, and from that you get the velocity drift, and then you can work backwards. So, and of course the magnetic field variation is not going to be large. It's just not going to be large, and I'll show you that in a moment. All right, so this is the basic premise of what I'm talking about here. We look at Zeeman splitting, and then we look at the velocity drift. And here is an example of that velocity drift, and this is the ones that are corrected for Jupiter and Saturn. And you can see here the trend lines show that the two brightest features at 6035 here in blue have the exact same, or they look to the naked eye, they look like they're drifting together. And likewise, the second brightest features in 6035 also have the same velocity drift. They're red shifting versus the others that are blue shifting. The fact that they're doing different velocities tells us they're in different volumes of gas. That's the first thing that's interesting. The second thing is we can clearly identify those two. If I go backwards, the red one's really interesting. I'll tell you why. So let's look here. Look down here. That's the red lines I just showed you. They're superimposed. So it's telling us that if they're by the methodology of spot maps, it's a Zeeman pair. And my velocity drift method tells me that, yes, that's probably 100% correct. So it's a further confirmation that these are Zeeman pairs. And we can do this for all hydroxyl masers. Okay? We can do this for anything. We can do it for methanol, for that matter, even if it's not has any hyperfine splitting. Anyways, the other interesting thing you see in this graph is this undulation. And as I said earlier, the Earth does not go around the sun in a circular orbit. And this is the Earth not going around the sun in a circular orbit. So it just gives you confidence that your accuracy of your fitting of your velocities is extremely high, of the order of 1.5 meters per second, or much better. These are 1 sigma errors, by the way, and this is 1.5 meters per second, which is what we calculate for the correction one would have to apply for the Earth going around the sun in an eccentric orbit. Okay, so I'm just showing you this to give you an example, a taste of exactly what you must correct for in your data as you go to this kind of accuracy. And understand something. I got funky y-axis, never mind. I missed my label for +1 and -1, but never mind. Maybe I did this early in the morning or after a heavy session out at the parties or something. But anyways, the upshot of the story is that we're down to literally 3 meters per second, whereas the velocity resolution of my spectra is 44 meters per second. So, and I'm only winning because of the trends. So I can see this simply because of the trends. I don't necessarily believe the errors, actually. I think they're a bit artificial. It's part of the Gaussian fitting routines. And I'm not necessarily confident with them. So really these 1 sigmas, I really should apply 3 sigma. But as I said to you, it's the trends. We're using the geodesy methodology now, okay? And so the trends tell us that the velocity drifts of the various Zeeman pairs are the same, and therefore they're likely Zeeman pairs, more confident so. Now, if I want to measure magnetic fields, of course, they can't be identical. Okay, because if there's a magnetic field, as I showed in my model, they have to diverge from constant. Obviously, we get that. And if that magnetic field is varying, in other words, it's changing over time, delta B is not 0, then the variation will be some slope different than this. And once you de-Gauss, because the R and the L will be affected identically, but in opposite directions as you apply a stronger magnetic field or weaker, then when you de-Gauss, you'll be able to find the motion and be able to subtract it out. Okay. Now, even if this wasn't a linear, even if it wasn't linearly regressing, okay, we can still use this method. It's just at the time series. And in fact, I've seen possible evidence of where the velocity drift is no longer drifting. And that could be due to a host of things. It could be the result of a new feature turning on that interferes with the one you're selecting. Remember, when we do single dish astronomy, we're choosing velocity features. In other words, an extent of velocity channels, and then we fit a Gaussian to it, okay? But that velocity feature may not be a single maser. It may be comprised of multiple masers. So it's important to keep these kind of things in mind when you're doing this method, because I can tell you something, ground state OH is incredibly maser rich, just as methanol is incredibly maser rich. And so you generally are not fitting a single maser, you're fitting multiple masers. And if they're in the same volume of gas, you might see the velocity drift being the same in all, or you're seeing an averaging of it. So that will skew your results very quickly. So there's lots of weaknesses to this method, but it can work, as you can see in this case. So for excited OH, something we don't normally talk about, it's less maser rich, especially 6030, by the way, because it has generally just 1 or 2 features. Wait, and I'll go back and I'll show you that in the spectra. So here's 6030. This is RFI, by the way, at Hafner. This is RFI, okay? And something else I should point out. In this graph, there's a huge gap in my observing here, not because I decided to go to sleep and not do observing for a couple years. It's because some idiot turned on a weather station opposite Hafner. All of this data is done by Hardebierstock, okay? And someone turned on a weather station. They weren't allowed to, but they were using this very nice, clean frequency domain of 6 gigahertz. And of course, it caused great difficulties. And then one day, I won't say who, but somebody went over there and sorted out the weather station, and basically it no longer operates. If you see newer data, they've now fixed it, regrettably, and I no longer live there. And again, I won't say who did it. But yeah, sometimes astronomy can be a little bit more than simply observing. Just don't do it. Don't do this at home. I'm not going to take any real pleasure in these things. Anyway, so now that I have two Zeeman pairs and they look like their velocity drifts are almost identical, that's how I identify them. And I also subtract out the effect of the Earth going around the sun. I don't have to, I just got to subtract R from L. That would just add a larger error to it, okay? And then you can finally look at magnetic fields. So we're using hydroxyl molecule to measure the variance in the magnetic fields, both in excited OH and ground state OH. And here in the blue is the 6035. This maser feature has been around since the 1960s, since the discovery of masers. So I have data going back on this particular source to 1965 in hydroxyl, okay? I don't have it in this graph, but I mean, I've reconstructed that from historical images, and I'm able to add those magnetic field points in, and it's very stable. This thing suggests that the magnetic field variance is 2.5 microgauss per day. So it's very small. And you see the slopes of the variance of the magnetic field in the excited OH to the ground state OH as being almost the same, which is kind of interesting. So they're in it might be that they're in a bulk cloud, a bulk gas that's moving through another medium where the magnetic field is getting weaker, or in this case, getting stronger. So that's entirely possible too. Now, as I said at the beginning, you have to take all of this with a bit of a grain of salt, because you have to disentangle line blended features in your velocity, in the velocity features that you've chosen. So as I said, I just believe the trends necessarily. I wouldn't believe an individual observation, okay? So hopefully everything is sort of moving in the same direction. So even if there's two masers there, they're both in this similar magnetic fields, and what I'm seeing here would be an averaging of those two magnetic fields, which would be quite close to each other. Again, I'm hoping that's the case. So really, we have to monitor this stuff in interferometry mode, okay? So that's the crazy idea. We really do have to monitor in interferometry mode where we know the position absolutely, and we can look for proper motion. And remember, proper motion is just in the plane of the sky, which of course is wrong, because nothing is just moving in the plane of the skies. It's either moving partly towards us or away. It'll be some sort of 360-degree effect. So your proper motion, when you do this, you get the Doppler shift gives you the, into and out of the page line of sight, right? So that gives you the 3 dimensions you need to actually really fully study these variances. And if we do this in interferometry mode, I believe we'll probably be able to create maps of and we could start mapping out the actual cloudlets, or the clouds themselves, and even the maser cloudlets for that matter. So we're getting to a spot where we probably can do a great deal more science with our even our single dish OH masers, and that's what I'm sort of trying to look for. As I said, I went from theoretical pure to now purely observational, and this is a purely observer doing this, okay? Right? So basically, Zeeman pairs can be identified using velocity drift. That's effectively what I'm saying. Or confirmed. Let's say confirmed, because I can tell those objects are Zeeman pairs by the spot maps, and now I'm just looking at, and by the way, this is our calibrator at Hartrail. So our calibrator is not very good, right? And in fact, we discovered the flaring, the accretion event in G9, this source NGC6334F. We discovered the accretion event in this source. Okay, that was there's only 4 major accretion events discovered, and we were using 6035 when we discovered that, not methanol. So in fact, these observations right here, I have an earlier observation from 2013, and I noticed that a feature had turned on, a new one had turned on here around 2015 here. And I thought, hey, I should monitor this. And I thought, I am monitoring this in methanol. And then we went back and looked at the methanol, and we discovered this massive explosion of the masers themselves in a new velocity extent. So that's how we discovered. We used hydroxyl to find the flaring in NGC 634. I can't talk properly today, sorry. Anyways, but in this source here, NGC, we used hydroxyl to discover the flaring that resulted in the only the second maser that had gone through a major accretion event. And something else that's interesting, and I'm going to show it now, my bonus slide, is this. So this is a feature from the 1665 LCP masers that I was monitoring. And again, these were my calibrators. We were using this in Sharmila Goodhart's periodicity program, looking for periodic methanol masers. And this is the hydroxyl side of it. This is a calibrator, if you can imagine. You can see I fit a Gaussian to it, so I have flux, line width, and velocity. And the thing that's most important in this case is that the flux started increasing in this Gaussian fitting at about 2013, not 2015 here. This is where methanol started increasing. So this was the birth of the flaring I had assumed in my first paper in 2017 or 2019, whatever, that the methanol started increasing in flux at January 1, 2025, 29, January 1, 2015, and it reached a maximum in August of 2015. And then the black line represents where the 12.2 actually went to zero. Okay, so the 12.2 didn't last very long. The 6.7 gigahertz methanol is still flaring in this velocity extent. But you can see here, it looks like the flaring in 1665 started 2 years earlier than the methanol. And I didn't know that. I looked at this graph, oh geez, really very early on, and I just said, no, I can't explain this. So I left it out of the paper. I just left it. I said, out the hell with it, which is probably not a good thing to do. It's not good science, but you know, that's what I did. But what it's probably telling us is this might be proof of the preheating of the disk before the accretion event occurs. So in fact, Anita, your monitoring program at Parks may be the savior for identifying earlier the accretion events that might occur in the future. Occur in the future. And let me be clear, there's only been 4 major accretion events in the first 5 years, from 2013 to 2019. We had 4 accretion events. Since then, we've had 0. Okay, and we now look at something like 500 methanol masers. So if we can find a method that will detect the flaring even earlier than when the methanol turns on, this would be very important. And I think the ground state OH is doing this in this particular instance. And so I just had a meeting. In fact, quite honestly, I didn't even know any of this until, when was it? Wednesday? Yeah, on Wednesday, I had a meeting with the guys at the Cork conference, and Alicio and a whole bunch of others were there. And we were talking about doing an observation on James Webb with this source because we want to look at the what's happening, because it's still flaring, right, in methanol. And I said, well, here, here's a picture of my OH. And I realized, and they said, well, this could be evidence of the preheating of the maser. So effectively, when the gas and dust is falling through the disk of the star forming region, it actually starts heating up the gas and dust, and it could create the conditions in which a maser can form. And this may be proof of that. Let's say it like that. This may be proof of that. So hydroxyl, I think, is going to become very important in the near future for being an early detection methodology for massive accretion events. So I want to end it there. Thank you. And I rambled a bit, sorry. But yeah, this is what I've been working on for the past, 30 years. And I hope it was informative. Thank you.
That was fantastic. Thank you. Thank you so much for that, Gordon. We've got Max has already jumped in with his hand up.
Yeah, thanks. Thanks, Gordon, for a great talk. Was very interesting. And what I want to say is to comment on this, accurate velocity corrections and things like that, because we've done something like that in monitoring of class 1 methanol. I did present it on the last Maser workshop, but unfortunately, it's still not published properly. So one of the findings was that, yeah, obviously models which existed in default software were not good enough. And there was very different, models of the Earth rotation and whatever, like to correct velocity, because it's not just the Earth orbital motions or rotations. There are heaps of weak effects, as you mentioned. But we ended up using AstroPy model, and essentially replace whatever is default model with that. And that worked reasonably well. So there were a few other minor effects / bugs in software which were unrelated to the model, but they took like another couple of years to find. So that's why I was blaming model, because I was seeing the sine waves at 1 year period. So it took me a while to actually convince myself that it's not the model, it's something else, and looked for bugs in other places. And as a result, I basically verified that model against pulsars and other things. So I have reasonably good confidence that it's good down to, I don't know, 10 centimeters per second level or something like that, whatever the authors claim. And yeah, I would definitely recommend doing that, because it takes out definitely the effect of ellipticity of orbit and GR effect. So that's fine. So I do have a reasonably good, well, that maser happened to be stable, and that's why I investigated every single outlier or any periodicity which was looking like it was in the data. The source was the periodic maser in class 2, so that's why we search for periodic variability in class 1. So there is some residual at the period which may be close to class 2, but it's 2 sigma effect, so I wouldn't really insist that it is there, but there is a possibility, or there could be a situation, because like one of the byproducts is the components are very simple. So although we know that there are hyperfine transitions in methanol, the split is bigger than even the spectral resolution of what I achieve. So not like, let alone the fitting and other things. So I suspect we have reasonably good grounds to say that if the hyperfine splitting is happening, only one component is emitting in this particular maser. So we didn't detect any polarization, which was interesting, but it's supposed to be shifting, reacting to magnetic field and things like that. So in principle, there could be the effect of this periodicity could be caused by changing magnetic field, but it's sort of hand-wavy arguments. Yeah, but anyway, yeah, the point I want to say is that look at AstroPi model if it's not what you are using, because it will take lots of worries out of equation.
Yeah, thank you. And yes, I hope to do that. Let me just say one thing on this. First off, on this graph you're seeing here, I did all this by hand, okay? So every single epoch, there's 500 epochs in this baby, and it is painful, okay? It's painful. And you can see the velocity was nice and constant at about a 7.5, and it suddenly changed. And there's this weird feature right here, which I find really interesting to me. Really interesting, because it dips, then rises, and it overshoots, and it comes back down. And I have to fix. I have actually looked at AstroPi. I haven't used it, and thank you for suggesting that. I will go back and look at it again. I'm computer illiterate, to be honest. I'm completely useless. I've literally forgotten most of the stuff I've done.
Yeah, I can just send you the script. You can modify to suit your needs. That's probably the best.
Thank you. I'll give that Max. I'll give that a shot, because I think we should be able to see more in our data sets. These are protoplanetary star. These are proto star systems. Okay. So what if they're binaries, and what if you have a binary system orbiting? Then we'll see gravitational effects from that, and we might see it in the velocity drift if we get down to centimetric levels. So, and of course, they discovered exoplanets at 7 meters per second, and we're already below that. All right. So I think we're at the precipice of finding more science in our data sets. These long data sets produce incredible amounts of knowledge. And as I said, this one, I can use this to try to identify the RCP component. So I'm going to use my same idea about velocity drift. In this case, I'm just going to use the flux density, and I'm going to try to identify the RCP component, which I haven't been able to do for the last, 10 years. So thank you. Yeah, that'd be very helpful, Max. Thank you. I see there's other hands, Anita.
Yeah. Malcolm?
Yeah, so I think we do understand the splitting factors in OH, and the difficulty with 1720 and 1612 is that you've got a different splitting factor in the upper and lower levels. So you actually get 3 different splittings. And I think what people have done in the past is that they've gone, oh well, the brightest, well, the one with the biggest A value is dominant. And I think maybe now people don't totally believe that, and have started, as you say, sort of averaging over the 3 different splittings in some sort of weighted way, probably to give you an agreement with the magnetic fields determined through the main lines, which are unambiguous. So I don't think there's actually any sort of new physics in there, probably.
Oh, no, first off, thank you for suggesting that I still remember some physics. Malcolm. So because I've forgotten so much, I think I'm pre Einstein at this point, maybe even a little bit more almost back to Newton. But what I was suggesting by this is that this is an interesting laboratory to test this. Okay, so I think we have to go. I was actually talking to an astrochemist here in China, and I was saying, look, maybe we should actually go and test this in a laboratory with more modern equipment and do it again, right? Because when were these calculations done? When did they actually do the physical measurements in a laboratory with under controlled conditions and vary the magnetic field, et cetera, and do the Zeeman splitting? I mean, we can do these experiments now and do a much better job. But isn't this an interesting laboratory to work with, right? And the question then would be, sorry, go ahead, Malcolm.
No, go on, carry on.
Oh, sorry. And so actually what you've just suggested to be an interesting experiment, because if they are because I totally forgotten that part about there are actually 3 lines, there's 3 versions, whatever. And the thing is that if we have a laboratory in which we find co-propagating masers such as these 2 here at 2 different transitions, okay? What I'm actually talking about is we can actually confirm what the Zeeman splitting is from the ratios. So we would know that the ratio between 60-30, 60-35 of the Zeeman splitting, we can just divide, the 2 numbers from each other, 0.079 divided by I can't remember what it is now. So it's there on my graph. But the point is I can actually get a ratio from this data set if I assume they were co-propagating, right? And so basically I actually just before I wrote this talk, I actually thought that's what I was seeing, that there was a difference, because I expect the magnetic field to be identical in co-propagating masers, right? And that's the laboratory we're looking for. And I thought this was the case for this source. And now I'm not too confident of that after making corrections for the planets. So after correcting for the planets, I now don't think that's the case. But out there somewhere in our, up above our head are objects that may have exactly the conditions we need to test what we're talking about, Malcolm. And I think it's interesting. It's an interesting experiment. It's expensive. It takes a lot of observing time, and it takes a lot of your lifetime, quite frankly. Like I said, this is 30 odd years. So yeah, it's interesting. But thank you. Yeah, I'd forgotten about the fact that it was 3 hyperfine splitting lines, etc. I don't remember that stuff.
So just one more question. Do you always see the trend of the magnetic field decaying, or do you ever see cases where it's increasing?
Yes, in fact, in this very same source, I could show you an example of the 1720 maser. So this one here, which again is not maser rich, it is the magnetic field is trending the opposite way. Okay. So actually both are getting stronger, but one's getting stronger, more positive, and the other one's getting stronger, more negative. Is that right? Actually, well, whatever. But it's getting strong. It's changing. And of course, because I can go back to the Weaver et al. Data from the 1960s, I have this incredibly long data set of 60 years we can look at. And there's big error bars, of course, right? I didn't show you the error bars in this data set. But they would be extensive, right? So, you believe what you want. In fact, I think if we get more accurate, we'll start seeing structure in the magnetic field variance. I don't believe you're going to see linear variance in the magnetic field. I think you're going to see structure in it, because I don't believe the environment that the masers reside in is smooth. This idea of 1 over r squared density in your cloudlet maser in your star forming region, I think that's a load of BS. I think it's a load of BS. I think it should be more dense towards the center, But the stuff by Burns et al. That showed there was a spiral structure, for instance, I think that gives us some indication that there's at least structure in the disk of the star, and these will reside in clouds outside that. And I think those clouds are probably clumpy, to be honest with you. And maybe this method here can help us become a tool for measuring the density variances in the star forming clouds itself. Kind of bizarre, but that's a longer term thing, and we need much higher accuracies, both in velocity. Thanks, Max, for the suggestion. I hope that I find that should be helpful. And then, of course, we need more sensitivity. The Parkes telescope is 65 meters, right? 64 meters. Sorry, it's grown a meter in the last 60 years. But HART is only 26 meters. And the telescope I'm using here at Nanshan in China is 26 meters. Okay, so you've got a much greater sensitivity, and we can drive down these errors further. So yeah, Malcolm, I think that if we can improve some of this value, we can use this as a laboratory to actually physically measure the Zeeman splitting coefficients. And we may find that in some instances, the different splitting levels are actually working in some and not the other. Wouldn't that be cool?
Yeah, okay, all right.
Got a couple other hands up. Michael Ruckel.
Hey, this is Michael. Thanks for the talk. I had a question on the other plot on NGC 6334F where you see the flare. Yeah, that one. So I was wondering about this rather large change in velocity. Do you have interferometric measurements before and after this change? Like, can you confirm that it is at the same position, or is it actually, could it be a different parcel of gas switching on?
Yes, well, and I thank you for asking the question. It's one of those things that drives me nuts, because I asked when we were doing the VLA observations of this source, I said to them, do the hydroxyl. And they go, no, it's too difficult, too much RFI. And I'm like, what? Drove me nuts. So the answer to your question is no, I do not. So I can't say. But you are 100% right. There is velocity confusion here. I'll tell you, you can see it in the data. So here, for example, the maser is happily going along for the first year or so at minus 7.5 something, and then suddenly something happens and it jumps up to minus 7.2 something. Well, that jump is not motion. That's not motion. It's just two masers. So one suddenly turned on that was brighter than the other, and it causes remember, I'm just fitting a single Gaussian, and that single Gaussian is now made up of at least two components. Okay? So all that's happening, and I've actually modeled this. Mike, I spent the last year and a half looking at this data, and I had to create models to explain the velocity drift I'm seeing. And actually, I'm able to now, this is going to sound bizarre, but I have in the methanol, I have three masers that comprise the brightest feature. This is in G9.62. And I've got three masers that make up the velocity feature that I'm choosing. That's the brightest. That's 7,000 Janskis. Okay? And what I do is I look at these light curves that I see in flux, line width, and velocity, and I fit models to explain the light curves. And from it, I can disentangle the three masers inside a single velocity feature. And I can tell you with some confidence, this idea of using a velocity channel or integrated flux to determine the light curve, the flare profile of periodic masers is wrong. Don't use it. Don't use it. It's wrong. It gives you an averaging. If they're all acting the same way, it's going to work perfectly well. But the reality is we're finding that there's two populations of profiles in G9.62. One is very fast rising and then a short, sharp drop, and the other is it's a long tail decay. So we have two different populations. I haven't published any of this stuff because I've been working on it for years. And when you're unemployed and you're living in Canada working with your brothers carrying stone in a masonry company, you don't have a lot of time to write papers, just so you know. So anyways, back to your question. Firstly, the velocity jump is the result of two masers in the same Gaussian fit. okay? And all that's happened is when the flaring started happening, one became much brighter, and it suddenly shifted the velocity over. Okay, so what is interesting to me is this drop, because this is actually a funny S curve. It kind of looks like this. Ooh, what did I just do? What did I just do? Okay, sorry. Let me go back in. Sorry. I'm playing with. I prefer doing these talks in person, to be honest with you, because then I can be more animated. I'm a little bit boring when I'm just talking on a screen and you can't see what I'm talking about. Let's go back. Okay, so it has this funny drop and then it rises up, it overshoots and it drops back down. You can see that right here in this area, okay? That part is bizarre, okay? The fact that the velocity went from here to here, that to me, I understand. That's just one feature becomes more dominant than the other, okay? So the velocity that I'm fitting a Gaussian to shifts slightly. That's all it is. So you're 100% right to ask that, Michael.
Sorry,
But
but the component at minus 7.5, does it disappear?
no, it doesn't disappear, but it's actually in this, it's in the fit. So the velocity I'm using here is probably not minus 0.3. This is an averaging of whatever the maser looks like, the Gaussian fits. So you still have that feature there, but I can't disentangle it, right? So
Okay.
I only have one Gaussian, and you can see it's here. It's, what is it? The line width goes from, it actually narrows, if you could imagine. Because it got so bright, the line, it's trying to fit a Gaussian that's quite narrow, okay? I'm only fitting a single
see.
Gaussian, Michael. Yeah. And so yes, that maser did not turn off. It's still there. It's just superimposed on each other in the velocity field. All right. So I don't know. They're definitely in two different parts of the sky, and they're probably separated by about 4 arc seconds, because I know that from the early LBA observations of this source. Okay. So you're absolutely right there, right? So no, it's still there. It's just that one is dominating.
Okay, thank you.
Yeah.
Michael Bush?
Yeah, thank you, Gordon. This is very interesting. I learned a lot. This is not what I do with OH, so this is super cool. But I had a very basic question, just to make sure I'm following with I think the slide before this, you had two different OH, yes, so the 6 gigahertz and the 1.6 gigahertz, right? Why are the absolute value of the magnetic fields different? Can you remind me?
Okay, well, in this case, it's probably because they're in two different positions on the sky. And let's go back to the spot map. So the one is coming from here, and the other is coming from here. So this is hydroxyl 1665, 3 and 8. So here's 3 and here's 8. And then the other one is in here. It's the, what is it? The 2125 from down here. It's these two here. Okay.
Okay, I thought they were the same parcel of gas. So I was a bit
No, I
confused.
wish they were. No, Michael, I wish they were. If they were, this would be the laboratory I could use to test the ideas that
right,
that
you're
talked
talking
about. Yeah.
Right.
Yeah.
Yeah, that would be a great experiment. Yeah, for sure.
Yeah, it's just, and so we're sitting on this stuff, guys, and we got to find an example of this.
Do you think an example exists in the current data?
I used to. I actually literally up until, was it Monday? Up until last weekend, I thought this was an example. Okay, I thought this was an example, and then I corrected for the planets, and then I did not think this was the example, because of course their velocity drifts are slightly different between the two pairs. So if I didn't even show the velocity drifts of these things. I didn't want to kill you with all sorts of data. Sorry, I didn't want to get crazy. But the velocity drifts of these two are actually slightly different to each other, which tells me they're not associated. Okay, because 1819 is 6030 and 2125. So here's 1819 and here's 2125. So they do lie very near to each other, but I don't think they lie in the same volume of gas. They have a slightly different velocity drift. So I can disentangle that. So up until last weekend, I honestly thought they were.
Interesting. And I think people here do Gaussian decomposition all the time. I think Anita and I and Michael, we would love to help fit multiple Gaussians probably to get that, because that next plot is very interesting with the different flares. I think you can see, I mean, the data goes from 50 to 100 Janskis, but it then goes back down to what, 50 Janskis in your last plot. So that is just superimposed, right? So
Yeah. Now the interesting part is this, is that, and this is the thing is interesting, is that when the flaring occurred, and I wished I should have showed another picture of another hydroxyl feature. It's very active around this period here. It's very active here. And then it just goes flat. It just goes quiet. And then it turns on. Okay? So if I was to show you another feature, another maser would show, that's actually in my publication. And you can see there's flaring going on 2 or 3 years before in another feature. Then it just goes radio quiet. And then it goes into its flare mode of the accretion event of 2015. And so does that tell us that the region's becoming unstable much earlier? And if that's the case, what's happening here? Because this region here is starting to become unstable. So it looks like it's starting to act up again. And is that a signature for a potential future accretion event? Now, something I published in the last paper, and I believe this is all BS, by the way, not this, but I made a prediction that in 2026, this feature would flare again. Okay, so I based that on the flaring of 1965, the flaring of 1999, and the flaring of 2015, and they looked like they were cycling down. They were getting closer and closer. So I had a simple model which predicted 2026. But of course, I think that's all BS, quite honestly. But it is interesting if we're seeing, I'm trying to stop. Normally, I will swear a lot, and I'm trying to not swear. So please bear with me if something slips out. But here the hydroxyl is now starting to get a little funky again. It's starting to get a bit more active. So is this a precursor for a quiescent phase and then an onset of a flare? I don't know. And so I'm trying to find things like that. Again, as I said, I don't know if I believe that, but that's what I saw. I just believe what my eyes see. Okay. But yeah, the answer to your question is, yeah, that would be great. I mean, I've been fitting this stuff with Gaussians now for the last couple of years. It's a process. Like this has to be done because of the RFI. OH has to be done, literally by hand. There's no automation. Whereas the methanol, I can automate it.
Okay, yeah. Yeah, that's interesting. You mentioned about that scatter. I see before the flare, it's very, well, the scatter is very low in the flux, but then after even it's quite janky, right? So I don't know.
Yeah.
It looks interesting. Maybe we
If you
can
look at, go ahead.
maybe if we do see the flare in 2026, then what we need to do is look at the scatter of potential
I'll be
maser
a-
sources as a
I'll be a
precursor.
freaking hero if we see a flare in 2026. I'll tell you. But no, I will take no real credit for it. I mean, really, it's just a guess. You write something in 2017, you think, yeah, whatever. That's years later. I'll be dead by then. But if I look at the 12.2, just as a matter of interest for this source, this is Hartrail's calibrator. So this is our
Oh, wow.
calibrator, right? So this is a problem, right? So our
That's a
calibrator
problem.
got really weird, right? And this huge accretion event occurred. So it's no longer a calibrator, obviously. But the 12.2, I do the Gaussian fitting for it. And only one feature, I see what looks like periodicity. So it looks like periodicity has turned on after the 12.2, after the flaring event. So this black line actually tells you where all the 12.2 turned off. Well, it turns out that years later, sometime around 20, I don't know, this is 2020, I think. What is that? 18, 20, 22. It looks like it's now flaring. It looks like it's now periodic in 12.2 gigahertz.
Wow,
Only
okay.
12.2. It's just weird. So, there's so much, these data sets are so rich with knowledge.
So you think that the flaring might affect the scatter here that we see? I mean, that's really cool. Yeah.
It's entirely possible that this is part of that, yes. But I can't prove, I have to clean it up more before I say absolutely that it's periodic, okay?
Well, we
So
should
I'm
let, oh, sorry, yeah. We
Go
have
ahead.
other questions. I just
Yeah.
want to make sure
Okay.
we get to the other questions. I think Jay's next.
Yeah, thanks, Michael. Hey, Gordon. It's lovely to meet you after 6 years of my first email to you, even though it's virtual. It's awesome that you these plots. And one thing that really intrigued me a lot is about your the statement that you said that OH started flaring, there's something funky started happening in OH couple of years before it started, in the methanol. I remember from maybe you can correct me on that, from the Todd Hunter and Crystal Brogan's papers on the source is before the methanol started flaring, there was continuum burst in 1.3 millimeter, if I'm remembering it right. That was also at the start or maybe end of 2014 or at the start of 2015. So you're saying that the OH activity or OH started behaving up and down even before that when the continuum outburst happened.
Yes, I can't remember. That's a good question. To be honest with you, I never read my own papers. I don't normally read at all. So I can't remember really exactly. I did edit that, but I do know that they're flaring. They had observations. It was pure serendipity, to be honest with you, because I had discovered that the masers were flaring after January 2015, and they had done a dust emission observation. They had SMA data pre-2015, and they had done a dust emission observation on ALMA in 2015, exactly when the masers reached their maximum. So actually they had two data points. So it's kind of difficult to say, they were going from very weak to very bright, and their brightest feature, my lips aren't working this morning. They're rented. I'm taking them back. Damn it, people. Anyways, technology today, they got to fix that. But so their observation of the dust on ALMA was done, I think, in August of 2015, and they had an SMA observation in 2013. I think that's the numbers, okay? But the answer is it had to have increased between then and there. We just don't know how that increased because they didn't monitor, which is a real crying shame. So they used my masers as a methodology, right? So they just assumed that the dust was increasing from January 2015 because that's when my masers started getting bright. Well, this actually is something we started noticing, but I hadn't fully convinced myself until very recently, had started increasing much earlier. Okay, so yeah, I think the timeline is something like that. I stand to be corrected. As I said, I don't read. And so I don't even think I read that paper entirely. I think I just read the abstract. Don't hold it against me. I don't know. I'm too full of energy and I can't sit long enough to read things.
Yeah,
But sorry, Jay, but yeah, I think it's something like that. But yes, the dust is also, right? So we should expect preheating, but nobody monitors on ALMA. Could you imagine applying for observing time on ALMA to ask for weekly or monthly? And they would look at you and they just slap you. They would slap you. There's no way you'd get observing time. And in fact, if I had proposed, we started our monitoring in 1992 in Hartrea, okay, in methanol. And of course, back in the day, I had methanol bias. It was so strong, so easy to monitor. And I just ignored hydroxyl. And I apologize, Anita. I just ignored hydroxyl, right? And that's a bias that we astronomers have. There's all these biases in astronomy. And for a lot of us, it's methanol versus hydroxyl. We tend to do methanol because it's easy. And I got lazy. I was playing too much rugby. I didn't have enough time to do hydroxyl and methanol. And so I just did methanol. Anyways, and that's what led to Sharmila then improving the cadence of our observing that led to her great discovery of periodicity in the first place. But hydroxyl, we should have been doing even further. And I had looked at a source back then that had some change. But if I'd gone to my boss and said, listen, George, if I want to do a 30-year study of monitoring, what do you think he would have said to me? You know what I mean? No, exactly. So yeah, no, it's really unfortunate. We need a time domain machine. I say this all the time. We need to monitor in interferometry mode. And we need to monitor at all transitions, not just hydroxyl, all transitions, all the time, and as many sources as possible. And that's the goal we have to strive towards, right? So we as single dish astronomers are just trying to tease new knowledge out of what we get. And we only get epochs. We get one or two snippets. We get like I said, this is it. I'll show you. Where's that image? That's it. So this is a snapshot that I got on an interferometer, the VLA, okay? And the point is, and I think there was one before that from the LBA. I think it was Caswell et al. Yeah, Jim Caswell was a great astronomer, a great astronomer. Okay, and but the point I'm trying to get at is, you know, we only get snippets on interferometry, so we get to do the hard slog, all of this work, long-term monitoring, and then they take all the credit because they produce this nice, pretty picture. Anyways, yeah, I hope they can give you the observing time on ALMA to monitor. I hope you live long enough to see people monitoring masers, monitoring dust in ALMA. That would be really cool to compare the two, right? But that's really the goal we have to get to. I think there's more science, and we don't do a good enough job. We just don't.
Well, don't be too much apologetic about observing methanol. Methanol is awesome. We all love methanol. So, and the other thing is that now you are in one of those LBA papers, so you can't be too, like, against on the LBA interferometric maps
No,
yet.
no, no, no. You're right. You're right. No, no, I am not. I got to tell you. But I promise you, if we applied to the LBA and said we want to monitor, 30 masers, Anita, what would you say to that proposal? You're on the TAC, so
I wouldn't be
you see
allowed
what
in the room during the discussion because of conflict of interest.
Oh, shame, shame. What the heck? What the
Screaming from
heck?
outside the door, give me the time. I
Yeah,
wonder
no,
though,
no.
if I could jump in on this. I wonder, I mean, obviously that would be fantastic to have regular monitoring with interferometry. But I wonder if there's kind of a compromise that could potentially get some time, is if we identify, through another like single dish monitoring, because that's easier to get time. If we identify regions where we want to do follow-up in the spatial domain, to then do, once every 6 months, once a year,
Thank you.
touching in with these, I think that would, and with the backing of the data from the monitoring, of course, then we have to process it before we do the proposal, which is a whole other thing. But maybe that's a good compromise.
No, no, thank you. That's exactly what I recommended here in China. I was actually at a meeting, I don't know when it was, on Monday, I think. And I said to them, I mean, they're building a 110-meter telescope, right? So I said, well, we need to augment, right? So we do monitoring on the 26-meter, and then we do every 6 months, we do a epoch check on the more highly sensitive telescope. The same is true for interferometry, and I said that then as well. That would be the perfect example, Anita. So if we could bracket, and this is interesting because if we can bracket our observations and we see something happening, we can interpolate. We can interpolate. And if we think it's really exciting, we can convince the LBA to monitor more frequently, right? So I absolutely agree with you. 100% support a proposal like that. That would be a really good idea. But we have to convince them what we're doing is exciting science, that we're teasing out new physics, new not maybe not new physics, but we're seeing new and interesting things that people are going to get excited about, and all of that comes from us, But yes, I agree with you. I would do that. I just talked about exactly the same idea on the QTT telescope here, doing using the smaller telescope and then doing intermittent observations on the larger one. Same is true for interferometry. In fact, I was involved with the design of the African VLBI network, which is really not gone very far, regrettably. And in 2009, I was working for the South African government, and we literally developed the African VLBI network as a lobbying strategy to defeat you guys in Australia. Okay, I promise you, it was a lobbying strategy. I honestly never believed they would build the African VLBI network. But I said to them, I said, listen, because we had some problems getting our African partner countries to help. And why am I telling the story? Because when we finally designed the AVN, we wanted to monitor masers. So we actually were trying to build a time domain machine in interferometry mode, and we wanted to do masers. We wanted to do 6 gigahertz C-band at the very least. That would be our starting point. We wouldn't have started at L-band, which everybody seems to do. We would have started at 6 gigs, and we would have done excited OH and methanol. And that was our goal, was to do time domain science, especially on masers. So the AVN was initially designed and conceptualized to monitor masers in interferometry mode. And so I'm still trying to get it built. So I'm still trying to find ways to raise money to build the rest of the AVN. It would be my dream to build the AVN. In fact, you saw the initial picture. Why am I standing on Kilimanjaro? I went up Kilimanjaro to look for sites for telescopes for millimeter astronomy. Okay, I climbed that silly mountain twice, and it sucked. It sucked. It sucked. It was hard. I had a torn Achilles tendon in this picture because I was playing rugby the month before. I traveled to Tanzania with a group of astronomers to go up and do site selection, and I had tore my Achilles and I had to hobble up the mountain. Oh man, it sucked. But the point is, we wanted to build a time domain machine to monitor in interferometry mode. And your compromise is what I thought of too, Anita. So it's good that we're all on the same mindset. It makes sense. And that probably is something we could convince a time allocation committee of. I agree.
Sorry, just to not hog this conversation too long, but maybe we should talk about this outside when, like, more in person as well. Is the scenario that you suggested, that why OH measures were flared before the methanol ones, and I think if I remember your words is that when the so my understanding is that, like, something went in the protostar from the circumstellar disk, then there was continuum outburst happened, and that got heated up the surrounding clouds, and that had these methanol flaring started, or as I think James report now, the water major flaring and stuff. But I think you mentioning that in hydroxyl, it's when the gas was actually or the material was falling in, that had even before the continuum, or again, there's as you said, that there's still not clarity about when continuum happened or continuum outburst happened or when it doesn't, but it's when the gas was going in, had that had something to do with the hydroxyl
Yes.
thing really. And that's very interesting, that what, because when gas was going in, what made it to heat enough to have those major conditions achieve that it started mazing.
Actually, it's even worse than that. Actually, I saw this simulation, a hydrodynamic code. These guys showed, after I showed this, I was in a teleconference with some people at Cork, Ireland. I think it was Alicio. I can never pronounce his last name. I can't even pronounce my last name. It was Alicio and a bunch of others, Verena Wolf, etc. And they showed this hydrodynamic code that showed that the gas and dust that's falling in, that's accreting onto the star, actually swirls around through the star forming disk cloud or whatever, and that heats it up. So it's a form of preheating. So this is why I call it the preheating phase. And it's possible that this is the preheating phase right here. And they suggested that, and again, I'll leave this to the theory people, because I have no idea. I don't pay attention. The excitation temperatures of hydroxyl are lower than those for methanol. And so the conditions are better suited for them to turn on sooner. I think that's what they're saying. But more importantly, this is the interesting part. This source, MM1 in NGC, did not have any detectable radio continuum. So what the hell what is the background source that I'm amplifying? What are the seed photons? So if I'm having preheating, why do I have where are the seed photons coming from? So there's no hyperfine H2 region there. Hyperfine. There's no hypercompact H2 region there. So what is the background source that I'm amplifying? Is it just the cosmic background radiation that I'm amplifying? I don't know. And so that is an interesting question, even beyond the preheating idea, which is just somebody's model, simulation. So that's the part that gave me confidence. Their model gave me confidence that what I was seeing here was real. Okay, literally this week on Wednesday. Okay, so yeah, I'm with you on this. This is interesting, because then it tells us that hydroxyl, ground state hydroxyl, is a far better detector of the flaring events themselves.
Yeah, I think that'll definitely change the directions of the whole M2O group when they're looking for these flaring events.
Yes.
That those will be thrilled by that. I
Yes.
don't. Yeah.
Jay, I sat in a meeting with them back in, I don't know what the year it was. I have no idea. It was probably probably at Hard Trail, so 2018. And I said to these guys, I said, listen, they wanted this triggering mechanism using methanol, blah, blah, blah. And I'm going, yes, but there are other transitions, because you have to understand something. I discovered this flare in 60-30, 60-35. I didn't discover it in methanol. I discovered it in 60-30, 60-35. So it was a priori. I went back and looked at all of this long-term monitoring from 1999 on this source. That was in methanol for Sharmila's monitoring program. Okay. So it was pure serendipity. Anyways, I'll cut that short. But yeah, I mean, I think the ground state hydroxyl is an important trigger for determining when these things flare. And I really think what we're doing monitoring at ground state OH is important. I honestly believe we should be monitoring at as many transitions as possible. And that's what I do at Hartrail. So I spend a lot of my time processing this data, hydroxyl, water, methanol, and lots of transitions of each. It's crazy. It's a lot of data. I get at least 500 to 1,000 hours a year.
Wow.
Well, thank you so much, Gordon. If you're looking for somebody to help you with that data, I'm always happy to reduce some more measures. So
Well, man, then you're talking the right thing. Okay, well, I'll keep that in mind. Let me tell you. But besides, by the way, this is my hobby. I love looking at data, so I enjoy doing it. So I'm not complaining. I really enjoy looking at data. I hope you do too.
Yeah, so do I. I mean, so far in last 7
Good.
years. Okay, but cool.
Good.
Yeah, thank you so much. It's very informative talk. Yeah.
We should allow Shinji to ask his question.
You've been so patient.
That is so patient for us. Thank you so
Yeah,
much, Shinji.
I like this workshop because lots of time to ask questions.
Right.
Yeah, anyway, so my question was, do you have, for example, for this data plot, you don't have a RCP monitor?
The answer is no, I do. I do. I have RCP.
I'm just curious because you showed velocity gradient to identify Zeeman pairs.
Yes.
I wonder if amplitude variations can be also used to identify Zeeman pair, and yeah.
The answer is yes, of course. So what happened was I have LNRCP of my ground state OH masers as well, but they're very maser rich, and I haven't been able yet to identify which feature. In fact, I've actually just thought of a new method of figuring out which one it is. So what I'm doing now is I'm going back, looking at my dynamic spectra, and I'm going to draw lines on it that say, okay, 1 milligauss, 2 milligauss, whatever, what the velocity would be in RCP. And then I'm going to use that to sort of hone into where I think it is, and then I'm going to fit Gaussians. So no, absolutely right. Because in fact, like well, let me go back here. You see the 1665? Yeah, I have where's the RCP for that? Right here. So here's 1665 here. Here's 3 and here's 8. I monitor both these. I monitor both R and LCP. And from that, I can determine that these are a Zeeman pair. Okay. So yes, absolutely. It's just that it's so maser rich. And the flaring confused things. And it's worse than that. Because we have a 30 arc minute beam at Hartrail at 1665, you get other sources interfering. So there's a source NGC 6334B that also interferes with my data. And so it has this weird undulation caused by the VLSR correction being wrong. And it comes in and out of my image, and it confuses my spectra. So I have to try to disentangle that as well as disentangling different masers that are actually competing with each other. So I haven't yet identified it yet. I looked again yesterday, and I'm just starting now to do a third attempt. But I hope to identify the RCP component. Yes.
Yeah, so yeah, if you did interferometric observation like VLA, yeah, so you could ultimately identify the Zeeman pairs, but what fraction of an entire maser spot would you normally be able to identify as a Zeeman pair? Is that very few fractions, or even with
Are you
interferometric?
talking about? Are you referring to the interferometric
Yeah,
observations?
like VLA, yeah.
Well, I'll tell you, I don't do a lot of time looking at interferometry, except for the pretty spot maps. I never look. So I can't give you a perfect answer there, but we probably do resolve out a fair bit of the extended emission. Okay, and that's something else too. It's an interesting question. Thank you. I'm not fully I'm not the expert. I really am not an expert on interferometry. I did my PhD on 13 hours on the VLA and never looked at it again. But what I can tell you is I think what we're doing in interferometry is we're only looking at the bright spots. And we're ignoring the extended emission, and we're resolving it out. And I have a strong suspicion that the masons themselves, first off, they're not Gaussian, by the way. They have a distribution that's probably non-Gaussian. So that's the first problem with this. We make an assumption of Gaussians. We shouldn't do that. But it's the easiest, right? It's the easiest. So I'm lazy. I'm doing it the easy route. So the answer to your question is we're probably resolving out a fair bit, especially on very long baselines for ground state OH. But on the shorter ones, we should be okay, enough that we can say, okay, the spots are doing this. So I guess my answer is a little airy-fairy here. I'm not really being clear. It's because I'm not sure we really understand that.
Yeah, we certainly need more data and analysis. But yeah, also for Zeeman splitting, people normally talk about the bandwidth, splitting bandwidth to associate with the magnetic field. But I wonder if we can also learn anything from amplitude balance between within the pair. I don't know. Yeah, is it too unreliable? Is amplitude too unreliable to deduce any physical parameters?
I'm not sure. You talk about the flux, the comparing
flux,
the variances.
Yeah, flux variance. Yeah.
Yes, no, that's a good question too. The interesting part about the flux, especially if you're looking at something like water, which we are not, and this is an OH conference or workshop. The interesting thing about the flux is if you look at water as an example, you get huge variances in the flux density as a result of the attenuation from moisture in the air, correct? And it's difficult to correct for that. But we also see variances in our calibration, as you can see in this data set here. It might be that some of this variance is simply the weather. It could have rained. Like there's a rainy season in December in South Africa. And when it rains, of course, it's going to affect even 1665. Okay? So it makes it difficult, but I agree with you, not impossible. So I've heard, and I heard this from who was it, Tim Robichaud. He had said to me once, and I've never seen the paper, but he said to me one time at a conference, he said, Gordon, you don't necessarily have to have one-to-one variance of RCP to LCP. And so that's another issue, right? And of course, that makes sense because when you have the hyperfine splitting, you're at a slightly different velocity, frequency where you're detecting, and maybe the conditions in the cloud are not perfect for one over the other, or they're more preferential to one over the other. It's probably why we see 100% polarization sometimes, that the cloud conditions are just not good enough for both of them. So it just moves far enough that we don't get the velocity coherence necessary. Now, that's me talking the science, and like I said earlier, I've forgotten most of my science, so don't take that. But I think the answer to your question is, yes, we can use the amplitude. We can use the flux. It's just we have to be careful to allow for the errors. And you can see in my flux, there's a lot of noise, okay? There's a heck of a lot of noise in this data, right? So it makes it more difficult, whereas the velocity, and of course there's noise in it, but it's a lot tighter because when you fit a Gaussian, you're using all the data points. The flux itself varies, so the Gaussian will move up and down because of, rain events and things like this, weather events, but the shape doesn't change that much, okay? And as long as the noise in the channels isn't too bad, it's all about the same, you get the same shape. And the shape gives you line width and velocity, the Gaussian fit. And that's just been my experience working with the data for the past couple of years. I may be wrong, to be honest, but it's why I think the velocity is a much better detector of some of these things than the amplitude. Okay, but having said that, yes, I agree with you. By all means, what I'm looking for, to be frank with you, in this source, I'm looking at the amplitude, trying to find the RCP. I'm not even looking at the velocity, because if you think about it, the feature that my velocity may be interfered with may be totally different, and I will see something else in the velocity. So the velocity doesn't work as a good discriminator for which one's the RCP component to this. So I have to use the flux. So that's a lot of rambling. I'm basically saying, yes, the amplitude does help you. Yes.
All right, thanks. Yeah.
Because I
Thank
think
you.
the difficulty with a lot of this kind of analysis is when you're in a situation where it's not bleedingly obvious what the Zeeman pair is, when you have, one single feature.
Yeah.
And you've got a ton of features, and they're all the flux is varying. So yeah, it ends up kind of compounding. I've noticed in some of the preliminary analysis that I'm not going to show because I I couldn't find the plots fast enough. But when I decompose a relatively complicated spectra, I can kind of separate things out in terms of, yeah, their velocity and their width quite well. I wonder if the line width might actually be a good way to match Zeeman pairs.
Actually, what I do now is I actually kind of use all of them, but I got to tell you again, the line width will be the interesting thing about the line width, and this is where the physics comes into this story, right? Like we're looking at canonical ensembles of gas here, okay? And then we're actually we're applying a magnetic field to it, and we're getting this hyperfine splitting, we're getting our LNR, but the gases may not be, they may have a preferential frequency that they want to operate on. And so your line width might be different for the two. Okay? So it's just interesting. But we have a laboratory to test this. It's called the outer space. It's called our star forming regions. So the answer to your question is in your data. I think if you see two sources, you will find that their line widths are fairly close, actually, to be honest with you. But I have noticed differences. I have noticed variances. So, and likewise, the flux. I have, what is it? The one I was looking at. In fact, some of these I just looked at the other day. But you can see that the correlation between the RCP and the LCP flux is very good. Very good. Okay? But they're different. They're different. Okay? But I mean, there are differences. And I agree with you. I think the line width is an important determinant. When you're doing, I'll give you a different example. The easiest way to test what you're talking about is if you look at a periodic source, okay? When things are constant, everything is like this, okay? You only get two numbers. You get a ratio. That's it. You get two numbers that give you a ratio, okay? If things are variable, now you got lots of data. Look at this. If this was flat, which it is here, it doesn't tell me a heck of a lot because it just tells me the velocity is, whatever. But if it's constantly moving around, it gives you more information. So if you have a periodic source, you get this, you got an ephemeris, you know that the source is going up and down through some sort of profile, and then you see what the line width is doing in that. So if a source is varying, getting stronger, we sometimes believe that the line will narrow, broaden, and do all sorts of funky things. We can see that in this line profile during a flare cycle, and it repeats. So we can check it from flare cycle to flare cycle. Okay, so then I see exactly what you're saying. I see the line width is repeating itself. Its flare profile is the same all the time. Or it's actually, I lie, it's not exactly the same, but it's similar. And I'm actually kind of hoping I can use that to study the variances in the actual maser cloudlet. Because as the flare cycle changes, it tells me that something must be changing in the maser cloud itself, which is kind of cool. So now we can use our monitoring to study how we can actually study the maser cloud itself, which is what you're talking about by looking at the line width.
I wanted to interject. I see Malcolm just raised his hand to say that I wanted to give maybe Anita the last 40 minutes on that segue of variability and monitoring to move on to that data set. But Malcolm, do you have a quick question?
Well, it's more like another comment that one of the pumping routes I traced for ground state OH for 1665 involved radiation at about 120 microns, whereas I think for methanol you need sort of 60 or something. So if the radiation spectrum that's pumping this event actually hardens over time, you'd expect the OH to go first with the longer wavelength.
So there's our answer.
Yeah, possibly.
Yeah, I was kind of wondering about that. That 120 micron pathway, especially if it's dust heating causing this thing like in a disk.
Yeah.
But
Right.
well, thank you. And that's an excellent discussion. And Gordon, I felt like I I learned so much, like in just 6 slides.
I hope I didn't ramble.
No, I very much enjoyed it. I'm sure everyone else did. And please continue discussion on the Slack in session 16. But I think we should give Anita maybe the rest of the time plus the further discussion on the variability. So let's thank Gordon again. I'll clap for everybody.
How do I unshare?
That's a great question. I don't know if I can do that.
Yeah, I gotta try.
Oh, I think I could do that for you. Yes, I can do that for you.
Oh, good. Thank you. Thank you.
Okay, well, our next speaker is the SOC chair, Anita. So, Anita, you need probably no introduction at this point, so go ahead and take it away.
Cheers. I get no indication of what you can see. I assume you can see my slides and not my preview.
Looks good. Yep.
Yeah, cool. In the context of that great discussion that we just had with Gordon, I wish I could have rewritten my whole presentation based on that discussion, but I didn't have time. I added one slide, but I can do a lot of hand wavy and talking at the end to kind of fill in where all the things that popped into my head while he was talking. So this is actually a talk I did at the ASA like 2 or 3 years ago. So it's completely outdated, but it's also sort of a reflection of how much time I've been able to spend on this data in the intervening years. So most of the slides and the images that I have are just from the first 2 years of a 5-year monitoring project, and that's because I had a fabulously talented undergraduate student. Be inspired, any students that happen to be here. I had a really, really talented undergraduate student who helped me with the analysis of the first 2 years of this data set. So I'm very grateful to her for all the insights that I'm able to share. So this is a program, I think I explain it more on other slides. So the wider context of the monitoring program at Parks is the M2O collaboration. So a lot of people who are in this call are members of this organization, but so this is just putting in its wider context that there's this broader ecosystem of people who are really interested in masers. And of course, as Gordon mentioned, they are a little bit biased towards the methanol, but that's all right. That's all right. That's all right. So I tried to update some of these numbers, but I noticed that my recent paper wasn't included on the list of their publications. So this is there's probably greater than 28 published papers from this group. 3 of them in Nature Astronomy. I think most of those have the same first author. There's a couple of talented bright sparks in there. But really, it involves quite a lot of observatories on quite a lot of continents and quite a lot of sources that are regularly being monitored. The issue, though, this being in the context of OH, is of those 1,000 or so sources that are monitored, hydroxyl is sort of the redheaded stepchild. It has sort of the least number of monitored sources, and it's actually dominated by I can't call it my project, our project that I inherited from Jimmy Green. So the idea is that we're supposed to be able to have like rapid response for flares, but of course that can only happen if you can process the data in real time. So I'm gearing myself up to try and recruit for students. You'll probably notice I'll keep saying, but I don't have time for that. I don't have time for that. That's why I need to get people who have time. So the Australian contribution to the Maser Monitoring Organization is with the 64-meter Murdyang dish at Parks. The 5-year project was called M2P2, Maser Monitoring Parks Program. It was initially supposed to be 6 years, but it's becoming increasingly difficult to convince the TAC to allow me to keep going because there's so few publications with it. So I've retired this program in this semester, but I've reproposed for a new program, which I can talk about at the end, to take its place, but hopefully improve off of it. So the observations themselves, there's sort of a core of about 20 targets that we look at. The whole data set, like all of the targets were chosen based on surprise, surprise, methanol. There are some strong associations between the behavior of methanol masers and the behavior of hydroxyl masers. So we were trying, thanks, Jay. The source selection was to try and identify sources that had some weird time domain behavior. be that as it may. So that was from the multi-beam methanol survey. That was sort of the basis of the source selection there. So there's about 20 targets that we regularly monitor. Every year we ask for weekly observations. Every year they give us fortnightly observations. But plus we also have some slightly different observations that we sprinkle here and there. There's about 60 targets total that have been covered by the survey, but there's the 20 that we observe kind of every single time, and then there's 40 that we either add to the end of the list when there's a bit of extra time, or in the early days of the project, we had some 8-hour time slots where we would just monitor everything. So some of those only have sort of 6-monthly epochs. Also, we noticed from the publication of the first paper, and thanks to my beautiful undergraduate student, that's Ashi. I should keep saying her name so she can get credit for it. She's not here, but she's fabulous. If you see her name coming across asking to do a PhD with you, say yes. So she was able to recognize some sources that looked like they might have variability on shorter time scales than fortnightly. So we have, I think there's like 4 or 5 sources where we had another observing campaign and we looked at them much higher cadence. That didn't amount to anything, but still, it's fun. So we do have some where we looked at them every 12 hours for a couple of weeks. And you can imagine how awful those 2 weeks were for me. We observed the 4 transitions of hydroxyl, and there's also 7 transitions of CH, but we have full polarization, which is very, very nice. Yeah, and it's the 4 transitions of hydroxyl that I focus on because that's what's relevant to my work and what I'll discuss here. The CH observations, a lot of them are really overwhelmed by RFI, so they're a little bit tricky, and really in order to get a signal, you kind of have to stack the whole 5 years to do that, but that data set does exist. So the targets are pretty well spread out in galactic longitude. We're close to the galactic center here, but we kind of go out to, is that 280? The ones that are in the core group are a little bit more concentrated towards the core, and it's because they show more interesting behavior. So just this might be news to anyone who's here who isn't a maser person, but just quickly doing a little diagram of what we picture is going on when we look at these masers. If we have a high mass star forming region, we would expect those high mass stars to ionize their surroundings. And in that ionized gas, you get the free transitions, which could then be, you know, background radiation. But as Gordon points out, sometimes you don't even need that. But then within the molecular gas, sorry, I did label these things, get a photo dissociation region outside of that, and then you have sort of molecular gas. And I tried to make it not try to imply that it's spherical. It's always more complex than a simple diagram can communicate. So there's OH. If you have some infrared pumping photons, then you can get some regions or pockets or cloudlets, or some people even refer to those as masers, those clouds, a wealth of different terminology, but you get these pockets of gas in which a population inversion is happening. So it's not a phenomenon that we tend to see across the entire region. It is kind of little pockets. And that's why when we look with the interferometry, they tend to resolve out into these individual spots. So when we observe those with a telescope, we're going to see any differences in velocity between those little cloudlets, and that's what's going to separate out their spectra. Additionally, of course, we can get the Zeeman splitting, which can also separate them out because we tend to look in the velocity space. But something I wanted to mention here is that the amplification of the background continuum of these masers is a relatively complex function of a bunch of different things, such as the infrared radiation field, column density, number density, velocity coherence, even the gas temperature, all sorts of different local conditions can determine how much the background gets amplified. And that's not even looking at how, you know, any changes in that background radiation, you know, if you're changing I naught, then the amount you amplify can stay constant and the brightness can still change. So it's a lot going on. So if I could give a bit of a summary of the things that we found in this data, we were trying to identify maser features. So that's individual features in the spectra. So that's why we've got 203 individual maser features. When I was telling you we only have a data set of about 60 masers. Those were maser regions or high mass star forming regions, and these are now the individual spectral features. We find that our data set is kind of dominated by variable sources in the 1665 transition, which is kind of interesting. I think that might be a function of how many features we identify at 1665. Therefore, the percentage of them might not be much different. But interestingly, the 1612 and 1720, finding variability in those because they're not really expected in the high mass star forming regions. They're not typical. They're not unheard of, but they're not typical. So to have a really, really big chunk of variable 1612 megahertz masers is an interesting result from this. Again, maybe for somebody else to analyze the data to find out what that is. We also tried to categorize the variability that we saw into sort of some broad types. This was when I was quite new to this field, so I might have stepped on some toes in terms of using long term, when people are out there with maser monitoring programs 60 years. And also flares might not be the right term either, but I'll try and define what I mean. But there's most of the variability. I mean, I think the purpose of this plot is that there's this other category, which is just weird variability that doesn't really seem to follow any clear trend. That definitely dominated, but we do have a lot of periodic features, which is fun. I'll show just some examples. So on the left here is this is just a random spectrum. I don't know who this is, but it's on the left, I have all of the spectra from the first 2 years plotted. So you can see that there is quite a wide range in intensity that we observe. But if you look at some of the other spectral features, like those that are kind of bundled around -38 kilometers per second, they don't change. So that's actually nice because it can kind of convince me that I'm doing the data reduction correctly. But we get quite a lot of variability with this one. If we were to track that peak over time, so all of those black dots, if we were to put them in the time domain, we see this sort of ramping up. And so I categorize this as a flare, which is kind of something going from sort of zero to something significant. Of course, then we also get the other side of this where we get things going down to zero. So that would have also counted as a flare. We also see some trends that don't really go to zero. It's not really clear what the shape of the trend is in time, but it definitely has a shape. It definitely is doing something. These two features are sort of not quite in lockstep, but even in their slight variations, there's some patterns there. Periodic, this was super interesting to me. We have quite a few that have very, very clear periodicity. This observation happens to be at the 1667. I know it because I'm working on this one quite a lot. This is my favorite region. But then the other category is, who knows what the heck this is? I don't know what this is. This is a particularly bright maser, but I don't know what that shape is. I always kind of thought it was like the cat ears. But if we can go back to this idea, like what we can get out of this data, or some of the things that we can get out of this data from my perspective. Obviously, there's all the really interesting stuff that Gordon mentioned, which I'll throw into the end because I don't have them in my slides. But if we remember that the amplification of these masers depends on sort of a complex interplay between all of these parameters, but you can kind of think of the physical ways in which these could change in a reasonable way, and just to start thinking of some ideas, perhaps in a given region, maybe the infrared radiation field might be constant, the velocity coherence might be constant, but maybe the column density varies between features. Maybe gas temperature and number density are changing over time. So this idea of if we've got like a shock coming through, you can start to speculate, you can start to get some ideas about which of these might be able to change between features, which of them might affect all of them equally, and we can start to actually constrain just because we happen to have a lot of features that are likely to be in at least a similar region at the same time. We might be able to use some molecular excitation modeling code like Malcolm's that he mentioned. What was that yesterday? It seems so far away. I'm losing track of the days. Or the MALPOP that Michael presented. And just the fact of having multiple features and multiple masers within a given region, it might help us to constrain some of these things. So I call that like a semi-controlled experiment. So while Gordon was talking, I tried to throw together some slides of some extremely preliminary results. So this is an example of two of the spectra. These are towards the same object. We got them at the 1612 and 1665, just to give you a bit of an idea of how complex and how many features we're looking at here. In the preliminary analysis that I put in this paper, we were only identifying peaks. We didn't do any Gaussian decomposition because we wanted to be able to get through the whole data set quickly and get an idea of the variability rather than characterizing individual features. But now that that's done and we're able to identify interesting regions, with the more interesting regions, which that I cropped this horribly, with the more interesting regions, I'm now fitting. So this is an example of Gaussian decomposition. I just grabbed this from my my own diagnostic plots, so apologies for like no axis labels or anything. But this is the spectrum in Stokes' eye at the top, right-hand circular polarization, then left-hand circular polarization and linear polarization. And then the bottom plot is a plot of the residuals of the fits. Trust me, if I were to put every single Gaussian feature in there, it'd be a horribly busy plot, but this is just from my own diagnostics. But from the Gaussian fitting, acknowledging, of course, that these features are probably not Gaussian, but I'm just trying to get a model, I might end up adding some of the fluxes together. I might end up looking at integrated flux. I don't know. But just as a first pass to try and find some interesting things, I made plots of every parameter versus every other parameter. And some of the things that I was looking for, I would love to see velocity changing over time, which might indicate magnetic fields changing over time. I didn't see that. And to the relatively high precision that I'm able to localize these guys in velocity, I didn't see that. I see some hints of maybe velocity dispersion changing over time, but that is then tricky because if you have a changing flux, it could, since the shape isn't really Gaussian, it might fit a wider Gaussian to accommodate that non-Gaussian shape. I don't know. So everything needs a little bit more care than just what I've done so far, which is plot everything against everything. But there is something super weird that I noticed, and I would love to get people's thoughts on this because I have no idea what's going on here. I find that for a majority of the features towards this region, when I plot the percentage of right-hand circular polarization or even left-hand circular polarization, but then when the y-axis is the percentage of linear polarization, I get these semicircular patterns. The colors here, it doesn't really mean anything. Each of those dots represents a different epoch, so they're a different day of observation. I just noticed with some of them, they happen to be clustered into little blobs. So I just assigned them a color so that I could see how they change. So the red dots in the top plot do correspond to the dates of the red dots in the bottom plot, but I don't know if they mean anything. They don't seem to be evenly distributed in time, so they don't seem to be a calibration issue. Some of the features don't show this relationship at all. So if it was a calibration thing, maybe I don't know. But I guess this kind of feeds into what Gordon was saying, is that these data sets, because I've got another 20 of these with the same time resolution, and I've got another 40 or so with fewer observations. And now this is only well, actually, I think this is more like 4 years of the data. But it's a 5-year project and it's just so rich. I have no idea what's going on, but leave that to the theorists. At least, the data is going to tell us something. So it's a really cool data set. I wanted to mention a follow-up observation that I just put the proposal in for like the week before last. Very busy times. So Gordon noticed towards this one high mass star forming region, which is G323.459, that the methanol masers in this region vary periodically. I think in that same paper, they also showed that the 1665 megahertz transition, which I have here from my observations, varies periodically. I can see in my observation, because I think somebody else said it was 1667. It might have been Jimmy. I can't remember who wrote that paper. But I also noticed the 1612 varies periodically. And it's like the holy grail of periodicity is when all of them have the same period. So all of the periodic features towards this source have the same period of about 90 days, 91, 92 days. But interestingly, in Gordon's paper in 2021, and then I noticed in my data as well, which I'm trying to illustrate here, there's a time lag in between. So there's like a phase difference in that periodicity between features. So these two features, this is, I think, the best visual example that I have because they have a similar flux. I have others that show the time lag, but you can't see them on the same plot. But I don't know if you can notice that the yellow, the triangles, they hit their peak a little bit earlier than the orange. And so that time lag, there's actually a couple of different groups of time lags. There seems to be about 4 different groups of maser features. If that time lag is whatever change in the pumping mechanism traveling towards these features at light speed and hitting some of them before it hits others, that could account for this because the scales in the region kind of match up with that. But it's super interesting because then if we can know what their distribution is spatially, we might be able to construct sort of a 3-dimensional picture of what's happening with the masers from this time lag. So we've proposed some new observations with the LBA, so the Australia Telescope National Facility Long Baseline Array, which includes telescopes all over Australia, with some pretty serious baselines that we should be able to resolve. Because there were some other LBA observations of this region, and they were able to resolve the masers with the LBA. There's been significant changes in the region since then, so that's why we want to look again. But again, I'm not necessarily trying to point out, this is the shining child within this data set. It's more of I've got lots and lots of these that I haven't really looked into, and there might be more insights and more things to gain from that. I'm just spruiking my paper because if you can't promote yourself, then who else will? But I wanted to just in like 13 minutes. I wanted to just briefly mention before we go into questions and discussion of what the new version of M2P2 is going to be. I very creatively called it M2P3, which is the Maser Monitoring Parks program with the PAF. So I'm hoping that the new CryoPath receiver, which is a phased array feed, so it has the capability of 72 beams and therefore a huge footprint. I've proposed in this last round a change in the monitoring program. So instead of doing spot monitoring that we've been doing for the last 5 years with the M2P2, to do a 72 beam scan across the galactic plane. And from my calculations, if they give me all the time, I should be able to in 4.5 hours per weekly or fortnightly or whatever they deign to give me, compared to the 4 hours that we have now. So our normal monitoring program is 4 hours, like every fortnight. I think, yeah, right? 4 hours? Yeah. Anyway, so moderate increase in time, and that'll result in a 10-fold increase in the number of masers we can monitor. And of course, the great thing about having a survey style monitoring campaign is we might be able to catch unknown masers. So the targeted one, of course, is only going to look at ones where we know are interesting. So hopefully something that's a bit of a more blanket approach could produce even more rich data. But of course, if you've got something scanning and moving, the interpretation of the data is going to be a bit complicated. So if anyone wants to do a PhD on this, I would love, love, love to speak to you. But that's it.
Thank you, Anita. That was an excellent talk. Yes, clap emojis for Anita. All right. Do we have questions, discussion points, comments? PhD students? Gordon, yep.
Am I up?
Yep, go ahead,
Oh,
go ahead.
thank you. Yeah, no, first off, Anita, you got to take credit for the fact that this is the first 1612 periodic methanol maser or hydroxyl maser. So this is from Parks. I mean, it's one I never did simply because we have so much, the RFI is so terrible. I said, bugger it. Anyways, and you have a much better telescope with more sensitivity, which helps. But yeah, you talk about the time lag. I actually, when I just looked at an image, I'm not going to share it. I can send it to you if you want. But we really should look at our data sets because I think I was seeing a time lag between the LCP and the RCP. Okay, in 1665 feature. It's entirely possible they're two separate features. Okay, and so I'm going to now use this new method I've been working on about velocity drift to see if the two are actually a Zeeman pair. I'm going to have to go back and see if they're Zeeman pairs. I'll go back and use some of the LBA interferometry data. But it would be interesting to see if that's the case because that tells us then something really weird's happening, you know, in your magnetic field.
I would struggle to trust any of that though, because that would almost make me think, oh well, then they're probably not the Zeeman pair. It's so hard to like, how do you convince yourself?
I don't.
I don't.
I just show data.
Just go with
I just show
it.
data. So all I did was I present the data to show that there's a time lag, and this is what you're seeing as well. You're seeing a time lag. And so the issue is, of course, because it's a flaring cycle every 90 days, we have an excellent laboratory in which to discuss to study that lag. So if we were able to do as you proposed, do multiple epochs across it, then we're going to have a beautiful look at precisely that, and in full Stokes. I mean, that was a dream of mine to do full Stokes monitoring for the last 30 years, and I haven't done it. Our telescope can't do it. And so, of course, we miss out seeing if the polarization is varying. In fact, Dirk Spitz, using the GBT, they're now submitting a paper where they're suggesting they're seeing, polarization variances, a 59-day period towards MONAR 2 in magnetic field variances. The polarization is changing. So is it methanol? I think it's methanol. So it's kind of weird. They're doing polarization studies, and they're showing a 59-day period for the magnetic field variations. So that would be the first time a magnetic field has a period to it.
Yeah. So are they seeing Zeeman pairs wiggling back and forth?
No, not. They're seeing Zeeman pairs, but you got to understand it's methanol, so the Zeeman splitting is incredibly small. So they got the methodology because they get such high velocity resolution on the GBT. They're down to 20 meters per second, and then of course when they fit Gaussians, they get down to something like 20 centimeters per second. Okay, so then they see that very sharp, very small separation. Anyways, just interesting, and of course, like I said, you're doing this in full Stokes. So you can look at the polarization variations. It may not be the magnetic field, but the polarization may be doing something weird. And that would be really cool. And that's why your LBA proposal is very interesting to me too. So yeah, the lags, as I said, I see this lag, but I don't think they're a Zeeman pair. So I'm going to check that though. But that was my main comment. That, and I want to say something I should have said in my own talk. Masers don't care. Whatever we think theory is telling us, the masers just do what they do. And you're absolutely 100% right. All of these things can change, causing these variations. Any one of them. And any one of them that changes can cause it. In fact, I remember, and I'll stop after this. They have 3 different models that predicts periodicity or explains periodicity. Each one of them is possible. And each one of them, I think I've seen evidence for. So masers don't care. So keep that in your head. It just reminds you to not get stuck on some dogma. That's all. Thank you.
Thanks for that, Gordon. Yeah, that's a really good point. And I feel like we're almost led to when we're publishing a paper, instead of saying this is what I think is going on, it's more of if this is what's going on, then that's how it would look. If this is what's going on. So yeah, I don't know if how much we'll be able to constrain things or what, but it's such a rich data set. Malcolm?
Yeah, so is the 1612 in phase with the methanol?
I don't know because I don't have simultaneous observations. I think I would have to
Right.
look at somebody else's monitoring
Okay.
data that covers the same dates to know that. I don't have that data. But yeah, that would be interesting. It has the same period at least.
Yeah, but I mean, the thing is that the methanol pumping range is, said to be sort of 30 to 60 microns, and the 1612, the sort of classic pumps there involve 35 and 53 micron pumping lines. So if it's all about the wavelength of the infrared radiation that's controlling the periodicity, then the methanol and the 1612 should sort of sample the same range of pumping wavelengths. Whereas you said that the 1665 could operate at softer radiation. So
yeah. All I can really say about that is the lags that I see in the OH are of a similar order, I guess, in terms of like numbers of days, but they don't match up with the data that was published in Gordon's paper. Was that 2021 with the methanol observations and the 1665? So that doesn't match up, but then our analysis pattern has been a bit different as well. But the time lags that they see in theirs, I do see in mine, but I also see other time lags.
Yeah.
I can't make too much of that at the moment because I don't know like the relative phase between mine and the methanol. But yeah, that would definitely be interesting to look at.
Yeah, so I'd sort of expect the 1665 to be shifted from the methanol, but the 1612 to be closer, I guess.
And it may very well be. Michael?
Yeah, hi Anita. Thank you very much. This was very inspiring. I had two questions. So one is in your in the diagram where you showed the distribution of variability between different lines. There was a small wedge of 1720 megahertz variable masers. Is that yeah? What are these? Like, does it follow similar patterns as the others?
That might be there might be two. Hold on, I would have to look at. Let me just paste the link to the paper in the chat because it'll be in there. It'll be in there.
No, I know your paper. I know.
Oh, okay. Yeah, I don't know off the top of my head. I would just be sitting here looking at the paper.
Okay, all right.
But it's not a significant number. It is not a significant number of 1720.
Okay.
And nor would we expect to see too much 1720. Yeah. But yeah, it's I wouldn't call it significant.
Okay. It's still interesting. Yeah, the other question which I had was so I'm involved in a project where we are planning an equivalent of an 18-meter telescope in Germany, mainly for test purposes. But so we were contemplating also to do a small science program and OH variability of OH masers, especially since we don't have too much collecting area, came to mind. So I was wondering how the M2O program works in detail. Like, is everybody observing the same sources, or do you, like how do you organize yourself, and what is like, are there requirements on the sensitivity? So do you need to have a 64 meter to join? Or
No.
yeah.
No. I think the answer to that question is it's probably not as organized as the aspirations of the people involved would want it to be. I'm not sure how these things have progressed because I changed institution and I lost all of my email contacts, so I kind of fell out of contact with them because I was part of the single dish network, right? And we had regular meetings to try and discuss strategy. So a first part of that was Ross Burns just compiled a list of who's looking at what. And there is a lot of overlap between the sources that people were monitoring. So this just happened naturally with no coordination because you're looking at the bright, interesting, weird ones. So part of the aspirations of that group is to use the geographical distribution of the telescopes to potentially monitor 24 hours, to be able to fill in some epochs, when it sets for one person, somebody else can monitor it. Of course, that implies, much higher cadence of monitoring observations. So I don't know. But so there is a degree of at least aspiration for coordination. But no, I would say, and maybe somebody, because there's a few people in here that are more active in that group than I am, so they might want to jump in, but I would say it's more of a loose consortium of like-minded people who are interested, and a lot of the conversations that go on in that group is people letting other people know about flaring events, mostly in methanol masers. So it seems like a lot of the collaboration between the group is trying to coordinate follow-ups of flaring events.
I see.
I imagine anyone who has a telescope would be more than welcome to join, because they're always interested in looking for more follow-up, particularly if you have a relatively flexible telescope where there's a flaring event, you can point it at it and have a look.
Okay. All right.
Because they might say, oh, methanol's flaring. Does anyone have any eyes on hydroxyl or on any other transitions to see if they're happening simultaneously?
Okay. Sounds good. All right. Thank you.
No worries. Gordon?
Thank you. I have a couple comments. The first one to Michael. Yes, the M2O clearly would be very happy to see you observe. I mean, that's why I'm sitting here in China. I'm helping them set up a monitoring program here, and I'm trying to encourage them now to move from methanol, which is what they want to do, to hydroxyl, all because of this. But yes, Anita, I agree with Anita 100%. The system is a bit of a loose organization, but they definitely want more telescopes, because more telescopes means we can look at more sources. Okay. The Ibaraki group in Japan, they look at 400 plus methanol masers only at LCP. So of course that's great. They have huge statistics, but they don't do the other transitions. The real goal was to look at the entire sky all the time at all transitions. So more telescopes means more chances of doing that. So please join the group, write to Ross Burns, who I think is responsible for it, join the group with your 18 meter. Very good idea. And that's what we're doing here.
He's at Riken at the moment? Is that?
Yes, he is. He's in Japan at Riken. Yes.
Okay. All right.
So yeah, no, definitely.
Right.
Yeah, no, definitely do that. Get a hold of them and join. Just join and just take part. Okay. Something about the 1720. It is a really strange animal. 1720 is very odd. This is just my experience. 17, and I bet you, Anita, you agree with me. It's just odd. It seems to do whatever the hell it wants to do, and it's like that child you have that's completely different than all the other children. Which I guess was me when I was a kid. But never mind. So yeah, 1720 is odd. It does a lot of weird things, and it doesn't vary like all the others. The 1612, I'm going to go back to Malcolm's comments for a second. I want to add to what Anita was saying. The 1612, we think it's more associated with something like some of the areas away, like people talk about it being in areas where there's outflow and stuff like that. I'm not sure about that, but what I can say is I've looked at this source that she was showing, and the OH is not in phase with the methanol. So at least in my data. Okay, 1665. The OH is not in phase. And so, of course, it would be nice to actually compare my monitoring with what Anita's doing. So Anita, you and I we really do need to sit down and actually collate this data, because we have so much, and we're the only guys in the Southern Hemisphere doing this stuff, right?
Yeah.
So I think the answer to Malcolm's comment is, I think it is out of phase, just slightly. I mean, I'm talking days, but it is just slightly different. That's part of the time lag that I saw, was between the OH and the methanol. And as I just said to you, it looks to me like the RCP and the LCP are are in. So you have some features that are in phase and others that are not. And my guess is it's not a Zeeman pair I just mentioned, but rather it's just that they're actually out of phase with the methanol, and they're different features. Yeah. So that was my comment I wanted to add in there. But thank you, Anita. Yeah, it's really, the variability is not easy. Your cat ears, by the way, I've seen something, I call it sitting dog. You know that position, what's that position in yoga where I don't know, I've never done yoga, but they do what's it called?
Downward dog?
Downward dog?
You're
I
like
have
a triangle?
graphs that look like downward dog and upward dog. I swear to you. And so I've now referred to all of my fitting as fitting elephants. So when I do modeling, I call it fitting elephants, and the couple of them, I actually call it fitting a herd of elephants. So I'm getting into that sort of phase of modeling, and it's just crazy. But yeah, I have downward dog. So you have kitty, I have downward dog.
That's interesting. These will make it into some papers eventually.
Hopefully. I got like one chuckle when I had that picture of the cat show up in the ASA meeting. I was very thankful to that person.
I'm gonna lean into
And
my ignorance
lastly,
here.
sorry, I want to add
sorry,
to
go
that,
ahead.
Anita. When I did that feature in NGC, it's the Cat's Paw Nebula.
Oh, nice.
I referred to the flare as Kitty. I always refer to as Kitty. Even in the paper, you'll see I refer to Kitty. So, and then I referred to the previous flares as, the mother. I forget what I called it, the mother and then grandmother of Kitty. So yeah, it was a silly play on words.
It makes your papers a pleasure to read, Gordon. I enjoy it. I appreciate it.
I'd always thought, if I could jump in on the excitation mechanics here, I'd always thought that we thought about the 1720 line anyway in the ISM as like tracers for shocks and supernova remnants and stuff, and people have said that they're amazing in those environments. But I think we just see, like in Splash and Joe Dawson's giant parks survey of OH in the galactic plane, like it's just amazing everywhere. So, as I mentioned earlier, it's like there's entire clouds that are just amazing in 1720. Maybe not even that brightly, a couple Kelvin or a couple, hundreds of millikelvin or something, but it's still anomalously excited. And I don't know, I've never modeled it myself. But yeah, so in my head I always thought, oh yeah, for these types of masers, of course, people always look for 1612, right? And then 1665 and 67, I guess the main lines have these very bright, transitions I hadn't considered. But yeah, it's interesting that you don't see the 1720. Maybe I just always thought though in my head that it would be insensitive to these sort of to me point sources, and that they just trace shocks and collisional excitation and not the radiative pathways that you would need for the other lines. But maybe that's completely wrong. I don't know. So
well, I think it's good to keep in mind that this is not a blind survey. It is a biased sample. We're targeting high mass star forming regions, so we would expect to see the mainline masers more. Not most, I shouldn't say most, a lot of the 1612 features that we've seen, they don't look like the kind of features that you would see in a high mass star forming region. A lot of them look like the kind of features you'd see in an evolved stellar atmosphere. So that's just like an incidental detection. So a good chunk of those 1612, maybe not half, maybe less than half, would then go away if you're not considering anything outside of the high mass star forming region. But yeah, this is kind of the breakdown that I would, I guess, naively expect to see if we were targeting the high mass star forming regions. But yeah, that's outside the context of if you look everywhere, you see 1720 everywhere. Yeah.
Right, yeah.
I think a lot of that, the 1720 that we see everywhere, I think a lot of it is the more Oh, I'm getting out of my area of expertise here, but there might also be a large contribution from yeah, the wider gas clouds that don't have this really strong pumping that we see in these high gain masers, but is more of a smeared effect over
Oh yeah,
Egypt. So that
Yeah.
might be skewing things. I don't know.
gotcha. Yeah, I mean, it's so interesting. We've got to disentangle this physics. Yes, sorry, go
Michael,
ahead.
let me just add to that. Anita, no, you're 100% right. I mean, remember, we tend to look at the mazes that are bright enough for us to observe, and we
Mhm.
don't look at the weak ones. So, of course, some of these transits and the satellite lines tend not to be that strong. So we tend to ignore it. And I think you're right about that. We have lots of sources, but 1720, I mean, the ones I've seen, they're just different. It's like they've gone their own way. Like everybody else is going one way, and they're going a different way. They are
Right.
seen it, like you said, you see them in things like supernova remnants. I had a person ask me, can we use them to look for black holes in dark clouds? And I thought that was really interesting. I never bothered following up on it, but it's
Mhm.
something that I've been talking about here in China is that, when you go to a much brighter telescope, it is possible, and I coined this new phrase. This is a cool phrase. I'm going to say it anyways, just for entertainment value. Fast maser bursters. So the simple reality is the environment in which masers reside can change rapidly. And people think, no, it can't. It can. All you need is a long enough path length for us, our telescopes, to detect. So even if it's bright enough, we get to detect it. So it may only occur for a very short period of time that you get that velocity coherence. And something like a black hole environment, people have looked. So we were hoping to look at the galactic center using Meerkat and SKA
Mhm.
for, OH molecules, for OH masers. So they may be turning on. And in our data, this is something we all can look for. In our data sets, we might have masers turning on and off that we just think is RFI. So it's only lasted a very short time. And because we integrate over, 4 or 5 minutes, we actually may be, weakening it so we don't actually see it. Or more importantly, we just don't believe it. Because how do you calibrate that, right?
Yeah, I was gonna say, how do you disentangle that? I mean, you have a line width, but then again, that's so narrow anyway. I don't know how you would
I'm
disentangle.
with you. I'm with you guys. I did it. I said it as a joke because I was telling these people, listen, if when we're tracking between sources, we can look for FRBs. So every day we lose about an hour to slew time. And so that slew time can be used for looking for FRBs. We don't necessarily need perfect pointing. We just need to know where in the sky we're looking, and it's just about detection. And then I started thinking, well, if I can find FRBs, why can't I find something like FMBs? And so then my mind goes wandering off. I'm the wrong person to have in a room because I will ramble for hours, and I'm doing it right now. But no, Anita, you're right. The 1720 is a really different animal. And I promise you, the ones that I've looked at, they always seem to do something different than the others. And yet they're in the same star forming region. And I'm thinking, how is this possible? But they seem to. So there's that.
Yeah, that's
Are
part
they?
of why I'm so hopeful that this proposal with the cryopath gets up, and not just the proposal, but the cryopath literally getting up into the telescope would also be a
That'd be
bonus.
nice.
For anyone
Um,
who doesn't know, it was my job to commission that thing, and my entire postdoc came and went, and it's still not up. Not my fault, not my fault. But yeah, to be able to catch those things that we're not necessarily expecting, that should be pretty exciting.
Yeah, we have to make our telescopes more serendipitous ready. So, right? Serendipity is the key to new discovery, obviously, because almost all the great discoveries were found through serendipity. We got lucky. We just got lucky. I mean, Pluto, it's a good example. So yeah, I think that when you're doing things like that, Anita, you're going to find really cool things. So the moment we say to ourselves, hydroxyl masers do this, we've actually limited our science, and we shouldn't do that.
Right,
And I
yep.
think your studies here, although not blind, are very, very close to what we should be doing on a larger scale. So
And well, I think hydroxyl is like luckily for us, strategically located right next to the 21 centimeter line. So there's loads of all these H1 surveys that just have hydroxyl in the wings, and they're just like, well, we don't have any OH people, but we have all this OH data. I mean, I don't know. Like
That was my
breakthrough.
PhD. That was literally my PhD.
Yeah, I mean, well, yeah,
I inherited
exactly.
everybody's. Because they're like,
So
it made their proposals look better. It's like, oh, well, look at H1. And also the OH, catch the molecular. which
Right. I think we
is
just
in.
piggyback off of 21 centimeter, and it's great. It's great. I do
Great.
enjoy it. Yeah. I recognize we're over time, so if anyone has dropped off or needs to leave, that's fine. Or we can wrap up too. Does anyone have any final discussions? I'll transcribe the chat and put it in the session channel in the Slack. Yeah. Otherwise, I'll just say thanks to Anita for a great talk. Let's thank Anita. And Anita, I'll pass it back to you. Any final things?
Oh, no. Aside from thank you and thank you everyone who attended. It's always so good to see this at least double digits in the participants. It's very gratifying.
Yes, and we're having so much awesome ideas being thrown around here, and I hope we encapsulate this somewhere. My hope is that we'll transcribe the chat and put ideas in the session channels, and at the end, I mean, the Slack will expire in 30 days. So after that, we'll have to coalesce all of our ideas in a document or something and put it on the website. But you know, hopefully this group that we have assembled we'll keep in touch through an email chain and the website and through efforts like this. So yeah, it's great. Okay, well, with that, thank you everybody, and I think we'll reconvene in what, two hours, or what is the schedule?
Yep.
Okay, for the next session, which if I scroll up is I think also OH Mazers and magnetic fields with Lucero as our speaker. So
Yeah.
yep.
Awesome.
All right, bye everyone.